keep my sound on so that I notice if there's any feedback. For some reason, I clicked my like mute button. I don't know. I was just rusty last time. Like if you rewatch the lab 0 and 1 videos, you can tell that like the audio is really bad because I forgot to mute everyone. As soon as I like that, whatever that is, I can't figure out. Let me see. So I know that I can mute everyone, but I don't know. It looks like everyone's muted. Maybe no. Oh, there we go. Okay. I think everyone's muted and I can't hear myself from anyone's computer because that's what I heard last time. And what I did was I just turned my volume off to eliminate the feedback. And that's not what you're supposed to do. You're supposed to mute the person because the computer's recording what I say, regardless of if my volume is coming out. So it'll be bad. And it's weird that it doesn't mute people upon entry. Like usually that's how it works. Yeah, I thought I did. Like you can, because this is just my personal meeting room. So like it's the same, like if you notice, like every office hours or whatever, it's the same link every single time. And I thought I set it like that. Maybe if someone else doesn't have it enabled, like they respect the user first and not the host. I don't know, weird. Okay, let's get started. Recording already. Share screen. Desktop. Cool. Go away. Make that thing go away. Make those go away. Okay. So the first weird thing in this lab is the system. So the system that we're using is these thingies. Over to the camera. Come out. Okay. Okay, so you set this thing up on your desk. I also can't see myself though. Why is that? How do I see just me? There we go. Maybe 10 and do 1. There we go. Okay, so now I can see what the computer is seeing. So this is your kind of the subject matter of what you're working with. And the whole lab consists of dropping it through these things called photogates. Photogates are things that shoot photons out of one side. If you see, there's like a little hole here. It's shooting a little laser through, and the other side is a photodetector. And so every time the laser is received by the thing, where is it? There's a light somewhere. Oh, of course, it's not plugged into anything. Maybe if I plug it into my computer, it'll work. No, that's not right. Anyway, there's a light right here, and it is blank when the laser shoots from this to there. If you put your hand in front of it, or for instance, one of these black dashes, so that the clear, the laser will go through and it will be received by its photodetector, but the laser will not go through when the black is there. And so every time the black is there, this light will flash. It'll say, I can see, I can see, I can't see, I can see, I can't see, I can see. And it's basically just telling itself something is passing in front of us, like we're being interrupted. So that's basically what you're doing for the whole lab. Some technical details. If you're like me and like your chair to be tall, you would like it to be down. So shrink all the way down, and you put your chair underneath where you're dropping it, because these things will break in half if they hit the floor. Not all the time, they're pretty resilient, but I have had, I think 2 people break it. There are more, but no. And you plug the thing back into the Logger Pro. This is the system, kind of like the external computer. And then you collect things on your computer right here. These are all plugged into these computers. So you use your little mouse and keyboard, and you log in. I believe it's just your net ID. So it's your net ID, and then whatever your net ID password is. These things should already be all set. And so now that this thing is plugged in, you can see the light flashing. Yeah. you can just put it. I was using that one before yeah, that's what you do. And you, as soon as you log in, there will be a folder in the bottom right-hand side of the desktop that says 121, 133 files. And you click on acceleration. That's the name of the lab, acceleration. And the reason I said you put this chair underneath is because it will bounce. You could, I guess, put like a folder or your backpack there so it doesn't bounce. But you want to drop it through your device. So the procedure is someone over here presses start collection up in the right-hand corner of the Logger Pro that you're seeing. And as soon as they press start, it's like a 1 minute, 1 second lag time. And then it starts recording data and you drop it through like this. And it kind of bounces. You do not want to take the data, all of this, good data, good data, good data. But mine jumped up exactly how I put it in. It went through. This is not good data. Don't take that. Only do this. If it does bounce through, that doesn't mean you can't use it. Just don't use the end part. Sometimes it'll bounce. Hit it. In general, you just want to have it as 90-degree angle-ish as possible and drop it straight through. In the first part of the lab, it doesn't matter how high you're dropping it from. I would just do right above. The second part of the lab, you're dropping it at 2 centimeters above, 4 centimeters, 6 centimeters, and that's way below. Anyway, so that's the actual what you're doing. So actual, like, this is more stereotypical of what you do for the rest of this course, not like measuring rectangles and stuff. So this is the first lab where you have a partner, you know, that's usually how it will be for the rest of the lab. I think all the other ones require partners. Anyway, so what does this thing mean? In the lab, you'll be asked for a couple quantities. One of them is D, one of them is capital N, one of them is lowercase d. So the screen sharing is explaining it right now. And what I did over here was I kind of copied this way, the pattern here. Small d, let's not do that. Let's just talk about what a pair is. A pair of segments is one clear segment and one black segment. So 1, 2, 3, 4, 5, 6. So n is the number of those pairs. So I have one pair. These little things are pairs. So pair, pair, pair. So n is 7. D is the length of all the pairs you need. So I started at this one. So I'm starting my measurement here at the beginning of my first pair, and I'm ending at the end of the last pair. So D is my whole distance, and N is the number of, they call it segments, I don't know why. It's usually pairs. I like pair better. But segment is fine because I guess they do it because Logger Pro gives you things in seconds. So for instance, when you are measuring your velocity and all that type of stuff in Excel, in Logger Pro, that's the system that measures things with this photo gate. It's going to give you velocity, not in meters per second like you're used to, but in segments per second. And so the whole point of measuring this thing is to get the length of the segments. And so what you do, because a segment is according to Excel, Logger Pro, a pair. So what you're doing when you get this, the length of the segment, you're doing the total distance. So this is the distance. You do it in meters or centimeters, whatever you want. And then this is just a number, the number of segments. And so the unit of D is length over segment. And the reason that's important is we can use that as a conversion factor. If the unit that they give in Logger Pro, I'll do DL, Logger Pro, is segments per second, we can multiply our conversion factor, small d, length times segment. And when we do that, the physical, which is what we see in real life, meters per second, the segments will cancel. So this numerator cancels with this denominator, and we're left with length over second, which is meters per second. So the formula is, in order to get a real velocity, you take your Logger Pro velocity and you multiply it by d. sorry, I didn't switch to the other. No. That is what I'm describing. So we have the units, logger pro, using the conversion factor here. We take the real or physical, real, whatever you want to call it, is segments per second. So logger pro right here, and we multiply it by our conversion factor D. And so that is how we convert, at least for the first part, velocity from logger pro into real stuff. For the second part, or actually still the first part, what you're going to be doing is getting A from your velocity graph. And the way we do this, this is kind of, in many ways, this is the answer to the discussion question. So this is kind of the standard relationship in physics. If you have a position, it's like the distance, x, centimeters, meters, whatever. If you want to get velocity, and your like position graph looks like, I don't know, that. So this is time, and this is x. So you're that far away from as time goes on. In order to get the velocity, what you're doing in terms of math is you're taking a derivative with respect to time. But in terms of every day, like what we're going to be doing is graphs. And that is the derivative is the same thing as the slope. If you write out the derivative in space in math, it is d, usually it's x, but in our case, our x of whatever some quantity in physical quantity. So the time and in our case is. So the time derivative of x, I can also write this in something called limits. Writing it like over the top like that. And if I look at a small limit, these little d's, so instead of interpreting it as a derivative, you can also interpret it as a small quantity. I'm going to say approximately equals delta x over delta t. If I look at that graph, this is nothing but rise or run from the algorithm. And that is exactly the slope. Y equals b. So, because the position is the derivative, the velocity is the derivative of position. In order to get velocity from an x versus t graph, we take the slope. Same thing for A, acceleration. So if we have a velocity graph, d over t, which you will have, you get that from logger pro. Something like a straight line. In order to get the acceleration, you do the exact same procedure. Replace this with b. That with a b, replace that with a b. It's still the slope. So A is dv over t, or the slope of a graph of v versus t. And so that's how you're getting acceleration in parking. You're taking the slope of your v versus t line. I don't even know if it's worth putting that on soon. It's kind of abysmally written. Anyway, so that's all part one. Part two. This is just a reminder that you don't have to use meters if you don't want to. You can measure all these things in centimeters. The only difference now is that the main result of this lab is finding the acceleration due to gravity on Earth. And in general, on Wikipedia and stuff, that's listed as 9.8 meters per second. If you measure things in centimeters, though, that's not right. You have to multiply that number by 100 because there's a conversion. You can barely see the dot on the Zoom, but there's a dot there. More from my first days. Yeah, there's a little dot there. Yeah, so you just have to convert If you measure in centimeters, you move the decimal place on the gravity 2 times. So it would be 980 centimeters per second. Let's see, what is this over here? Yeah, let's do this first. So you've probably seen it in your homework and stuff like that. These are the equations called the kinematics equations. So that's what we're doing right now. It's called kinematics, how things move, position, velocity, acceleration. And the equations are, if you want to find out the final velocity of some object, you take whatever the initial velocity is, and you add the acceleration times time. The way that these equations make sense to me is you take the units. You do something called dimensional analysis. The units of V are meters over seconds. The units of this V, meters over seconds, that fits. Now the units of A is, this is not right, meters per second squared. That's the definition of gravity. It's meters per second squared. And so these are, let me note this for a second. Do that. Text to the second power. Okay. What is that the computer? That's so long. Oh, wait. Okay, it's coming down now, I guess. So that was really weird. Anyway, kinematics are, that's so funny. So the reason I talk about units is if I mean, maybe it's not coming down. It's really weird. Anyway, so if the units of acceleration are meters per second squared, and I multiply that by a time. Yeah, it's definitely turn it off. Yeah, that's weird. I mean, maybe you guys can go through it. It's literally off. But yeah, that computer works just fine. You guys use that one. That was hilarious. So if the units of acceleration are a distance over time squared, and I multiply that by a time, one of those times cancels, and I get meters per second, which is the unit of velocity. And you can do that with all of these things. The same thing is for x. So meters per second times second is meters. So that one checks out. And acceleration is meters per second squared. So if I do 2 seconds, seconds to the second power, then I get another meter. Now the final one that we're going to be using today is if I want the velocity, the final velocity, if I square that quantity, and I also square the initial velocity, and I add 2 times the acceleration and the distance, it's fallen. So for instance, in our case, h is going to be our delta x, so delta x equals h. And v0 for us in particular is going to be 0, because when you drop things, you drop it from rest. We're not like throwing it through the thing. So v0 right now is 0. So as soon as I drop it, that's not 0. It's the time, whatever. And so if we simplify this equation, so what we're using in lab today, we have Vf, so V final, that's like the final speed at which this thing has accelerated, is 2 times g, because A, in this case, it's not like we're pressing the brakes on a car. This thing is free falling. So the only acceleration it's experiencing is gravity. So A here is g, delta x, we're just going to call it h, same exact thing. And so we have Vf squared equals 2gh. And the whole point of lab is to get the value of G. And so we're going to do the exact same thing that we did for last lab with the y equals ax squared and the a equals a over 3 x cubed. We're going to isolate the slope and solve for G. So in this case, we can plot this on the y-axis, this on the x-axis, and then this equation becomes exactly a y equals mx plus b graph. And then we use the fact that whatever slope we get from that plot is 2 times G. And so m equals, I forgot I can just handle things here. I should have been doing it more instead of writing over there. So m equals 2G, that figure. And so if we want to solve that, we say that G is 1/2 the slope. And so that is the final result. So in both cases of the lab, in the first one, you use the velocity graph and you get a measurement of acceleration from the slope of it. That one will be extremely accurate. And the reason for that is because you're taking multiple trials and you're letting the entire thing pass through and you're considering everything. So the result for part 1 will be very accurate. You'll probably get 9.8, 9.7, something like that. For the second one, it's going to be very hard because it's very hard to measure 2 centimeters above this thing. You have to measure from the dot, right? And that's like weird. There's no like, you have to measure how you're doing like this. So it's a very, there's a lot of error right there. And so the result for part 2 will be pretty bad. In general, how you get these quantities, H you measure, but what about VF? VF, where is it? Oh, here it is. I don't know why I said V0, that is VF. Okay, so what you'll see on your Logger Pro, there'll be five columns. There'll be a time. State is kind of an arbitrary thing that you need to worry about. 1 means it's blocked. 0 means you can see it. 1 means it's blocked. It's not, state is, you don't really need for the whole lab. Neither do you for distance. V is really the only thing you need to worry about for the whole lab. And time, of course. So time and velocity. And your first velocity that you measure, so that would be as you're dropping it through. As you're dropping it through, you are measuring the velocity of this. Yeah, so the velocity of this. So as you're dropping it through, the very first velocity that you measure is that. So you'll see there's nothing, nothing, and then something. The very first one you get, that's the defining. So instead of caring about the whole thing going through, we're actually, yeah, you are dropping it through, but you're only caring about the velocity of that first one. Okay, that is everything. Other than that, I'll just give you kind of a cheat sheet for what equations you need to use from the error PDF for each cell in the Excel file. It's still, uncertainties are still new to you, so I figured I'd just do the cheat sheet. This is I think those are all right. Let's F16. F16, yes, that's still right. Yeah, that's still right. Also, again, I have no idea what this R squared is. You can just ignore this whole section. I have no idea what they are. As you can see, mine doesn't have that from last year. I don't know who okayed this R² stuff, but anyway, we are ready. So start doing stuff, and I will get up again, screenshot, stop sharing, and then it'll, now that I know the audio wasn't bad, it'll be better to post. Stop recording.